Thank you. Well, appreciate you all being here this afternoon, and I want to thank you all for inviting me. That's my first time to Australia, and I'm having a great time and enjoying your country immensely. I have to apologize that you're going to realize as I'm giving my talk, first of all, I have a bad accent, so you have to bear with that. You also find out that all my units are wrong. We're still using the units that even the English don't use anymore. And you're going to find out that I talk about wells instead of bores. You know, where I come from, the bore is the person who talks about the wells. So you have to bear with me on that. And also, you know, this talk is something that I give to everything from lay people to drillers to, you know, technical people such as yourself. So it's kind of a broad overview. It's not real technical. There's nothing in here that you haven't already heard. Okay, but maybe they'll find something interesting here. So with that, let's see if I can get this to work. And no, there's a setting for this. Hang on. Let's see. No worries, she'll be right. That's the best part of the talk. You might as well go out. This is the William A. McEllhiney Distinguished Lecture Series. And I just want to say a word about Bill McEllhiney. He was the founder of the Illinois Groundwater Association that grew into the National Groundwater Association. So he's kind of the granddaddy of the National Groundwater Association. And if anybody has seen the journal Groundwater, you know, it basically that's a result of his efforts. So that's why they have this series in his honor. Because he was an engineer and a well driller, this series is kind of meant to bridge the gap between the practical and the applied. I also have a personal connection to Mr. McEllhiney. When I was an undergrad, I got a part-time job as like a little junior geologist with a well drilling contractor in Milwaukee, which is just north of Chicago, where he had his drilling company. And when I was just starting out, he was the kind of the go-to guy when our engineers would have a problem. They'd say, let's call Mac. Mac, you know, well, let's find out what Mac thinks we should do. So they'd always call this McEllhiney guy. I never got to meet him because he died 6 months after I started. But, you know, the fact that, you know, I kind of feel like he's sort of a mentor because I heard his name spoken in such reverence so many times. You know, even though I never got to meet him, I still feel a connection to him. And to be the McEllhiney Lecturer is kind of very rewarding for me. And as I said, this was started in 2000 by National Groundwater Association. And in 2005, Franklin Electric, here comes the plug, Franklin Electric started to sponsor this. So they're basically making it possible for, you know, for me to be here. And even if you don't like my talk, next year there's going to be a really good talk. So I just want to acknowledge that Franklin Electric is doing this for the industry, and it's very much appreciated. So what is sustainability? Well, first of all, I want to say that I've been really impressed with how sustainable Australia is. First of all, for instance, you're so sustainable, you even recycle your prime ministers. Okay, I won't use that one again. So what is the term sustainability? It's a very kind of fluffy term. It gets tossed around a lot. In the United States, it's kind of a political term. But you know, it has some general concepts that are useful. I just want to point out that your aquifer is the only part of the water system that you can't replace. So, you know, as a profession, are we maintaining our aquifers as well as we're maintaining, say, the pumps or the pipes? Probably not. And the other thing one common thing about all unsustainable systems is that they just don't last. So why do we care about sustainability? Well, it comes down to population. If you look at a plot of human population starting at about 10,000 BC going out to the future, and this is 0 to 20 billion. If we look at, say, starting at 10,000 BC going out to like the Stone Age to 3,000 BC, human population was very low, a few million people growing very, very slowly. Bronze Age to 2000 BC, still very slow growth. Iron Age on that same slow linear trend. Middle Ages starts to kick up a little bit, but still only a few hundred million people. When we get to the Industrial Age, it starts to spike. In 1804, we get to our first billion people. 1927, 120 some years later, second billion. 1960, 33 years later, our third billion. 1974, 14 years later, our fourth billion. 1987, 13 years later, our fifth billion. 1999, 12 years later, our sixth billion. So that first billion took probably over 100,000 years. We're now putting 1 billion people on the planet every 12 to 14 years. 2011, 7 billion. Where's it going? If you project that trend out to 2100, you could say as high as 16 billion. Okay? The UN looks at population growth, and they say that when societies get to be more affluent, their birth rates naturally fall. We're seeing that in North America. We're seeing that in Europe. We're even starting to see it in Asia, and we're starting to see it in Africa. So they're saying it's really more likely we'll have 10 billion or maybe 6 billion. So somewhere in the middle, around 8 or 9 billion, that's the optimistic view. So if you look at that change, that can be a step function. Okay, if we can support that population, out into the future, we just basically have gone through an almost instantaneous jump from a few 100 million people to somewhere around 8 or 9 billion people. That's a heck of an experiment to be carrying out on a global level. Is there enough water and food and resources for all those people? I guess that's the challenge of our age. So when you look at that plot, you can either look at that as a step function, or if you think back to biology class, talk about the experiment of taking a milk bottle and putting 2 fruit flies in it and sealing the top. And if you were careful enough to pick a male and a female fruit fly, the population ramps up very quickly in the milk bottle until they consume all the air and all the food, and then it starts to drop off. That's usually what they use to teach people about a bell curve. When you see that kind of rapid response in a population in nature, it's often followed by a rapid decline. Okay, so if you're a pessimist, you can talk about the fruit fly future. Okay, now I'm not suggesting that's going to happen, but I'm just saying that in nature, that's a common occurrence. So that kind of quick rise leads to a quick fall. So what's the difference here between the optimistic view and the fruit fly future? Well, you can call that difference technology or management or engineering or dumb luck. I'm going to call it the global IQ test. And by that, I mean collectively as a species, are we as smart as the fruit flies? So what are some definitions of sustainability? This is nice and short and sweet. The capacity to endure. Another one, equity over time. What I like about this one is it brings in the concept that for something to be sustainable, it must be fair. You can come up with a system and force it on people, but if they don't buy into it, if they don't think it's fair, they'll find a way to cheat that system, get around, or eventually overcome that system. So if something's going to be sustainable, it has to be perceived as fair. And this is a common definition that gets used. Sustainable development meets the needs of the present without compromising the ability of future generations to meet their own needs. Okay, once again, has to be fair over time. Okay, what are we talking about for water resources? Well, there's 332.5 million cubic miles of water on the Earth. Each cubic mile is 1.1 trillion gallons. Even in units you're not familiar with, that's a lot of water. So the message there's a mind-numbing amount of water on the planet. But 97.5% is in the oceans. Only 2.5% is fresh. So if we take this drop to represent all the water on the planet, that little sliver, 2.5%, that's all the fresh water. So if you pull that out into its own drop and you look at how the fresh water is divvied up, you'll see that something like 2/3 of the fresh water, 68.7%, is tied up in glaciers. Fairly remote, not really accessible to humans. This little sliver right down here, right there, less than 1%, that's all the surface water. So even though the average person, when they think about fresh water, they think about lakes and streams and dams and things like that, that's the smallest sliver of fresh water that's available to humans. Far and away, the largest amount of fresh water that's available to humans is this 30% that represents groundwater. Another way to look at it, if we just take the globe and we strip off all the water from the oceans, you can see how much of the planet is covered by ocean, over 70%. Okay. But if you take all the fresh water on the planet, it would fit into one ball with a diameter of 860 miles. So if you put that right on Denver, Colorado, it would fit in the western United States. Now, if you strip out the glaciers, we're only looking at groundwater and surface water, that's a ball with a diameter of 170 miles. So that would fit, say, in southern Indiana. If you just look at the surface water, the fresh surface water, that's a ball with a diameter of 35 miles. If you put that on Atlanta, Georgia, it would fit within the city limits. And if anybody knows about the water wars at Atlanta, they'd love to have it. But basically, I think if you look at it this way, you can kind of recognize that the fresh water that we have available to us as a planet is very finite. So we have to look at how we're going to manage it. And I'm going to refer a lot to this USGS Information Circular 1186. It's on groundwater sustainability. It's by Bill Alley. It's free on the internet. And it's very well written. It's written very simply, but some very good ideas and some very good graphics. So, you know, if you're looking for a good primer you can share with non-technical people, 1186 is a good one. And one of the concepts they talk about is, to be effective, groundwater management must consider environmental, social, and economic needs. So, you know, it's the old concept of the triple bottom line: people, planet, and profits. If you leave out any one of those three, it's not going to be sustainable. And one of the quotes from the publication is that because any use of groundwater changes the subsurface and surface environment, that is, the water must come from somewhere, the public should determine the trade-off between groundwater use and changes to the environment and set a threshold for what level of change becomes undesirable. You know, as I've been touring around Australia, I've been hearing kind of how you manage water. One of the stories that comes up is kind of the Murray-Darling Basin, where people started with a very top-down approach, and the irrigators basically rejected it. And now over the years, there's more of a cooperative approach, and you're renegotiating it all. This is the same thing we've gone through in the United States. We tried the top-down approach, and the local people fought it, rejected it, wouldn't do it. So now we're trying the bottom-up approach to get them involved and come up with something that they'll buy into. And as we look at managing groundwater, managing water, we have to recognize that groundwater has a very unique role. And that is basically, the aquifers are huge storage vessels. We went through a big dam building period in the 1900s, and I know you folks did too. So we built huge surface reservoirs for water storage. We're now finding out that that's not a very efficient way to store water. If anybody's ever flown over Las Vegas the last few years, and you've looked at Lake Mead behind the Hoover Dam, you see that big 80-foot tall bathtub ring. That's basically evaporite on the rock wall. That shows how far the water is down from the average water level. They were within, about a year or two ago, they were within 40 feet of losing the ability to produce electric power from Hoover Dam. The City of Las Vegas Southern Nevada Water Authority is drilling 2 large tunnels underneath Lake Mead to intercept the reservoir at the lowest point, because the water intakes are getting close to being exposed and will no longer be usable to get water to the city of Los Angeles. So the idea of storing more water on the surface, it's probably a thing of the past. It's very expensive, huge environmental footprint, not a very efficient way to store water. But we're probably coming into a period in human history where the need to store water is probably greater than it's ever been. So where are we going to find these new reservoir sites? Well, they're the aquifers beneath our feet, particularly in aquifers that have been depleted, where you've created large cones of depression. You've actually created storage volume for aquifer recharge. We have places in Southern California right now that are fighting over not who owns the water, but who owns the drawdown, who owns the cone of depression for water storage. kind of a change in thinking. And because I give this talk to some non-technical groups, I try to put some simple ideas out there. And one that I use is thinking about groundwater as nature's canteen. And that is basically when you have a wet year, like a canteen, groundwater can store the excess. So it stores water when you have extra. And in a dry year, groundwater discharges to the surface water, keeps the stream flowing. So just like a canteen, it gives water back when you need it. Like a canteen also, groundwater allows humans to live in areas where we normally couldn't live, away from surface water. There's a good book called Elixir, written by a gentleman named Fagan, and he was a archaeologist with University of California, Berkeley. And it's about man's history with water. And he talks about one of the oldest man-made structures that's ever been excavated. It's on the island of Cyprus. It's 9,000 years old. It's a hand-dug water well. So for over 9,000 years, our species has been using groundwater. And I think it's been a critical tool that's allowed us to expand out into regions we normally couldn't live. And I think it's a big reason why we've made it to 7 billion. Now, as hydrogeologists and professionals, we know it's not just a big canteen. You have to look at the geology of the aquifer too. And if this is a kind of a typical kind of a schematic of an aquifer where you've got an unconfined system, confining layer, and then a confined system, in some kind of recharge area, you get these local flow cells and intermediate flow cells. That can be days or years. And then you can get these large regional flow cells through the confined aquifer that could be centuries or millennium. The point is that water is always going from recharge to discharge. And you put a well in and pump it, you intercept that water on its path. So you will affect surface water discharge at some time, at some point. If it's a local flow cell, you'll see that impact fairly quickly. If it's one of these regional flow cells, that impact could take decades or more to see. For humans and their planning for infrastructure, things that happen within a few days or a few months, they can recognize that. Things that happened over decades, they have a hard time recognizing. They have a hard time factoring that into their planning. So another concept as we're talking about management is it's impossible to use a natural resource without impacting it. In the States, we have a lot of people who want to kind of take they want their big cars, they want their big house, but they want to say that the nature has to stay pristine. And they don't recognize the conflict there. Zero human impact means no human use. So the best we can do is to understand the impacts that we're going to have, minimize the impacts that we can, and manage the impacts that we can't minimize. We also have to recognize that all resources are finite. So management is going to happen. Okay, some resources can be replenished to some degree, but if you continue to take more of a resource every year, you will eventually come up to the limit of the resource. So you're going to have to limit, you have to manage your demand. So you either have to do that, you can do that early if you recognize the problem ahead of time and have the wisdom and the political will to make the sacrifices early. You can manage something sustainable that's more or less painless. We tend as a species to wait until there's a crisis. And then we have to manage out of dire emergency. And that's when there's conflict, and that's when people get upset. But we have to recognize when we're thinking about managing water that zero impact is not a practical nor even a desirable goal. In the U.S., we've had some aquifers that have had huge amounts of storage, and it's created an illusion of limitless supply. And I know you've got the Great Artesian Basin here and some other aquifers, but our history is like, for instance, the Ogallala in the Great Plains. This is a very heavy irrigation area. It's semi-arid, and the Ogallala is a very large aquifer. And I remember when I was a kid hearing people talk about the Ogallala as being a underground freshwater sea, a limitless source of water, inexhaustible water, more water than the Great Lakes, all these hyperbolas. Well, then I remember 10 or 20 years later them talking about, well, in fact, we got to lower pumps in some of these areas. Now, I was just in Kansas a couple months ago. They're talking about the end of irrigated agriculture in the state of Kansas within 50 years. It's a huge shift in the way they think. So, you know, we have these issues in the Ogallala. We have our coastal aquifers have been very heavily overpumped, and they're suffering from saltwater intrusion. In my neck of the woods, here in the Great Lakes region, Milwaukee's right there and Chicago's down here, we've got a very thick Cambrian Ordovician aquifer. It's confined locally, and it's a very good source of water, 2,000 feet thick. Initially, those wells flowed at 1,000 gallons a minute when they were drilled in the 1880s. We now have, in parts of the Chicago area, 800 feet of decline. So, you know, it's all over the country we're facing these issues. And this is a quote from the Kansas Geological Survey, a gentleman named McFarland. When you have these regional aquifers and you start to overpump them, the storage allows you to mine that aquifer for quite a while. So you build infrastructure and populations and economies based on mining that aquifer. When you find out that you're overpumping the aquifer, it's pretty much too late to stop. Okay? At that point, you can only really start thinking about management in terms of buying time to find an alternative. You'll never be able to live on the recharge rate of those aquifers, but you might be able to find an alternative. So the quote you hear from the Kansas Geological Survey is, "Sustainability may not be a viable management concept for confined aquifers." So there, you know, basically you can't keep overpumping an aquifer forever, but you need to buffer the economy for a transition period to find something that is sustainable, and that may take decades. So we have to recognize that many regions have been drawing down the groundwater canteen for decades. This is a quote from a former poet laureate of the United States. "Something can be wrong and still make sense. There's never a shortage of practical, hard-headed people making one wrong decision after another because it makes sense." So I'm not trying to be real cynical here or pessimistic, but if we go back to that example of the Ogallala, that is the part of the country that was hit in the 1930s by the Dust Bowl. And the Dust Bowl was a prolonged drought that was really exacerbated by really bad agricultural practices. And the soils dried up, and the wind blew, and prairie topsoils that had grown up, had built up over thousands of years, blew away in a period of a few years. They had dust storms that started in Kansas. It would blow all the way to Washington, D.C., 2,000 miles away. Farmhouses were buried in soil. People watched their neighbors starve to death, or people would actually get caught in the dust storms. They would suffocate on the dust. So these people went through hell. And then shortly thereafter, somebody came and told them that there's this new drilling technology and these new centrifugal pumps where we could tap this underground limitless sea, and your farm can be prosperous forever. They thought it was a godsend. So they went into it with both feet. Now, they overdeveloped it, and it only took them a couple of decades to overpump that aquifer. We look at it now and we think, that was a wrong decision. That didn't make any sense. What they knew at the time, it was the logical thing to do it. It was a wrong decision, but it made sense at the time. We have to remember now, we know more, we make better decisions, but we don't have perfect knowledge. And politically, we can't even use all the knowledge we already have. You know, there are things that we're doing now for managing water that we know are not sustainable, but politically we can't change them. So we have to be a little humble ourselves. 50 years from now, people look back at us and figure, what were you thinking? It wasn't sustainable. I mean, the plea here is for adaptive management and to learn and use what we've learned in our management strategy, which is not something that humans like to do. Humans resist information that does not conform with their preconceived ideas, or if it's information that threatens the status quo, we resist it. I sometimes think that the hardest substance on the planet is the human skull. It's got a hardness of 11. We need to get past that, and we need to start using what we know and be more flexible in our management. So what are some areas with sustainability? In the United States, these pink areas are large regional aquifers that have declining head. And they tend to be in the large population centers, and they tend to be in the very big agricultural areas. These blue dots are smaller aquifers that meet the same criteria. So really, it's all over the country. And if you look at the world map, the world situation, this is the areas at overall water risk from the Water Research Institute. And you can see it's pretty much where all the people are. So I used to say this was a global problem. I was corrected recently by Charles Fishman, who said all these water management problems are local. What we have is a local problem that's happening all over the world. So how do we manage water, groundwater in the United States? This is kind of an overview of some of the different approaches. We have 50 states. Every state does it differently. So most states are managing groundwater, but for many different goals. As of 2005, only about 30% of the states incorporated sustainability into water management. We have some of our states that are managing groundwater by monitoring freshwater discharge to surface water, and they're doing that to protect environmental flows. Examples are the state of Florida. We've got 5 groundwater management districts, and say the Edwards Aquifer Authority in Texas. These are places that have springs or other surface water features that are very important to their ecologies or their economies. So they manage groundwater by monitoring surface water, and when they see an impact on surface water, they cut back on groundwater pumping. There are other states that also recognize that connection between groundwater pumping and surface water impact, and they will manage it that way, but they are managing to protect senior surface water rights. That's an entirely different approach. An example of this would be tributary groundwater in Colorado. Colorado basically says that if you pump from an aquifer, that the water would normally discharge to surface water within 100 years, that aquifer is tributary to the surface water, to the stream. The water in that stream is fully appropriated. They've been appropriated for 100 years. So if you're going to pump that aquifer, you have to have a water right that's senior enough to let you take that surface water from your well. So there are large parts of Colorado that have had irrigation districts shut down because they were impacting senior surface water rights. There are other parts of the western U.S. that also recognize the connection between groundwater pumpage and surface water, and then by statute they ignore it. Okay, an example is Arizona. Arizona has a thing called subflow, which is groundwater that's immediately adjacent to a stream or surface water body, and it's recognized as being directly connected. Everything else, even if you're still in the same alluvial plain just a little further away, is percolating groundwater, and by statute it is not connected to surface water. Now, Arizona has some of the, well, it's kind of a crazy state, but they do have some of the best hydrogeologists in the whole country, and they know better. When they came up with this in the 80s, I thought basically, they had some very high-powered people that were supporting this. I thought they were basically just a bunch of hydrostitutes. I thought they were just, selling themselves out. But what they were trying to do is they recognized that the water rights in the basin are already spoken for. So if they were going to restrict groundwater pumping to protect senior surface water rights, there'd be no groundwater pumping. So to allow economic development to occur, they came up with this legal fiction. And the idea was to allow development to go on so you could build up a constituency and build up basically the economy that could afford to find alternatives. Colorado went through something similar that actually kind of opened my eyes a little bit. Colorado also has this concept called non-tributary groundwater, and that's confined basins where the water doesn't discharge to the surface water within 100 years. They used to let you take all that water you wanted. It led to, one of the major areas of the state with this is just the eastern suburbs and east of Denver. It's all on the large Denver-Julesburg basin. There were wells in the 1980s in some of the nicer suburbs. Water levels are dropping 40 feet a year. They're having huge cascading water problems. So they recognized it really wasn't sustainable. But there were no other water sources for these communities. So they came up with a law that basically said you could take 1% of the water in storage from your aquifer under your property per year. And when they first came up with that, I thought, they are purposely managing for depletion. How is that responsible? But what they were doing is they were stretching out the period of depletion. They were trying to limit how fast it could be depleted, and it bought them a few decades, and in those few decades, there's been enough economic development that the water is now valuable enough that they can afford to do things like water recycling, aquifer recharge, things that weren't viable in the 80s are happening now. And it was actually a logical bridge to a sustainable future. A lot of the states in the Midwest and the East, where it's a little more humid, are riparian states. And of course, riparian water law is the oldest water law. If you've got a piece of property adjacent to a stream, you have a right to that water to irrigate your land. It goes back to the Egyptians and the Babylonians. It's very old. When states started regulating groundwater, they considered groundwater to be riparian to your property, just riparian on the bottom. That meant you had a right to pump as much water as you wanted to. It was a property right. And in the United States, property rights are a really, really big deal. Unfortunately, it also led to what they call the law of the biggest pump. People would put in large wells with large pumps and use the water irresponsibly. There was a case in Texas where somebody was growing catfish from water from a large flowing artesian well, tens of millions of gallons a day, and it was drying up springs and it was drying up neighbors' wells. So most states have moved to what they call regulated riparian, where there's a test. You have a property right to pump as much water as you want, but there is a test saying it has to be a beneficial use and can't cause undue harm to your neighbors. So it's balancing the tangible property right of pumping the water versus a communal right of protecting the resource. And that's not something we do very well in the United States or never have. So out of this mismatch, there are some new models popping up that are really actually kind of interesting, and I think are kind of hybrids that point to the future. And Texas, actually, believe it or not, is one of the stars in this. They've been working for about the last 10 years to come up with a new groundwater management program. They used to be the principal bad actor for the law of the biggest pump. They defended that for decades until they got to the point where they basically couldn't go on that way anymore. So over the last 10 years, they divided the whole state up into water management areas, and then in each of those water management areas, they defined groundwater management districts based either on watersheds or counties or some way to do it. And the state then went and paid for groundwater area models, these GAMs, for every one of those groundwater management districts. So the whole state has got a groundwater model to work out the basin. And while that process was going on, they used the models to come up with what they called managed available groundwater. So they said, okay, how much groundwater is out there for each of these basins? And then they formed, in the water management districts, these little groups of irrigation districts and municipalities and business leaders and environmental groups, pretty much the big broad tent. And their goal is to set desired future conditions. And they're just finishing this process right now, where the local people look at the model, get the technical input from the state, look at how much of groundwater is available, and they decide, are we going to manage to have sustainability now? Are we going to have to manage to slow our rate of depletion and look for alternatives? But it's a local plan that the state enforces. So they're finally getting some buy-in. It's getting, certain self-interested parties are tying it up in court, and it's been very messy. But they're moving towards a sustainable future. And California is kind of a real mismatch, of ideas. California was strictly riparian, where you basically, in most of the state, you can pump as much water as you want to from your land. That very quickly led to basins that were basically being depleted. So they ended up in a whole bunch of lawsuits There's a good book on it called Dividing the Waters by Bloomquist, and he's an economist, so he talks kind of like how out of chaos theory, this group of self-interested people battling it out kind of led towards a consensus, and basin by basin, they've been negotiating their own water management strategies that fit their economy, the climate, and the politics of the basin. And they have actually recognized in the state of California more different water rights than any other state. They have riparian, appropriative, prescriptive, overlying, pueblo, and reserved rights. They all mean something different, and they all apply in one part of the state or another, but not all over the state. For instance, like pueblo water rights, they go back to the Spanish land grants from the 1600s. They're still honoring those. So what are some examples of what happens when you overpump groundwater? Well, this is a little stream in north central Wisconsin called the Little Plover River, and it's a trout stream. And in the Midwest, in the United States, trout streams are a big deal because you need very cold water, very clear water. Grown men like to go and crawl in their bellies and try to get these little fish. With the fly fishing, it's quite an ordeal, but they really value these trout streams. This stream also happens to be in an area with a nice sand and gravel aquifer, about 100 feet thick, very sandy soils, very easy to get 1,000 gallons a minute out of a well. It's also become a very large potato growing part of the country. So in the 50s, there were maybe a few irrigation wells. In the 70s, there were a few hundred. Today, there are tens of thousands in the 7-county region, and these things can pump over 1 million gallons a day. So in the late 1970s and the early 1980s, the USGS did one of their first finite difference models, and they looked at this basin. And they said, if you keep taking more groundwater, eventually you're going to dry up the Little Plover River. And it could happen as early as 2005. And actually, in 2005, the Little Plover River went dry for the first time. And it's gone dry every summer since then. And in 2013, this year, the Wild River Alliance or whatever basically named the Little Plover River as one of the most threatened rivers in the United States. And this, Wisconsin gets over 1 meter of precipitation a year. We have 15,000 lakes. They kind of fancy themselves to be the Saudi Arabia of water. So having trout streams go dry in Wisconsin has really changed how people think. The politicians had to notice. This has been in all the papers. So we spent the last 8 years fighting over our high-capacity well laws to try to balance that property right that the farmers have versus the common good to keep trout streams flowing. And it's not just Wisconsin. Here's a case in Massachusetts. This is the Ipswich River near Boston in a normal year. That's what happens in a drought, and that's from groundwater pumping. So they're also redoing their high-capacity well laws. So Kansas went through the same thing. Mario Sophocles from the Kansas Geological Survey has a quote. Basically says, we can maximize the yield of our water by drying up our streams, but when we do, we learn that the streams were more than just containers of usable water. This is a case from Florida. This is central Florida, a place called Crooked Lake, and it's kind of up around Tampa and Orlando. And that's what it looked like in 1970s. That's the same dock in 1990. Okay, that's not a drought. That's from groundwater pumping. Florida gets 2 meters of rain a year. 18 million people, almost all on groundwater. So they have heavy pumping, particularly around Orlando and Tampa. This is another case history, not far away, also around Orlando and Tampa. This is White Springs. Florida, if no one's ever seen them, Florida in the central northern part of the state has these large springs that can be well over 100 million gallons a day of blue, clear, crystal groundwater coming up out of the ground. They're beautiful. The old Tarzan movies were filmed in one of these springs in Florida. They have divers that have gone, miles, underground mapping these things. They're phenomenal natural resources. And in the 1900s, they built a bathhouse over one of these springs, so the spring would fill up this pool, and it would flow out into, into this lake. If you can imagine living someplace like Darwin before there was air conditioning, you would spend a lot of time at one of these springs, right? So this was a very popular social place in the 1900s. That's what it looks like today. And that's not from drought, that's from groundwater overpumpage. And in my little neck of the woods, this is Milwaukee, this is Chicago, this is Lake Michigan. The Great Lakes, the 5 Great Lakes, represent 20% of the fresh surface water on the planet. Chicago and Milwaukee are right on Lake Michigan, one of the larger of the Great Lakes. We have this thick Cambrian Ordovician aquifer, 2,000 feet thick. It's confined in this area. And when they started pumping in the 1880s, when they started drilling this aquifer, the wells would flow at 1,000 gallons a minute. Now, as of 1980, we had 400 feet of decline in the Milwaukee area, over 800 feet in Chicago. Today, that cone of depression is more like 500 feet in the Milwaukee area. So we've gone from flowing at 1,000 gallons per minute to having groundwater levels below sea level right next to the Great Lakes. We even have, we have water levels about, below sea level in portions of the aquifer underneath Lake Michigan. And the Ogallala we talked about. The Ogallala is basically sand and gravel that came off the Rockies in the Pleistocene. And it's anywhere from a few hundred feet to maybe 800 feet thick, depending upon where you are. So you can see it's kind of channels coming off the Rockies. This is what it looks like from space. Each one of these dots is a center pivot irrigation well. There are tens of thousands of these things. They're half a mile in diameter, and they all take hundreds of gallons a minute to irrigate. So it's a large aquifer. It covers parts of 7 states, and it's been very heavily drilled. This is the state of Kansas, and these are just the monitoring wells that they've put in to monitor water levels in the Ogallala. The USGS has called the Ogallala the most intensively used aquifer in the U.S., and it's also been called the single largest water management concern in the U.S. This is a blow-up of the water management district here in the northwest part of the state. And here are 2 monitoring wells that the USGS has been monitoring for 50 years, 80 to 100 feet of decline. Okay, there are parts of the Ogallala that are worse. There are parts that they think they may be within 20 years of depleting. But clearly, it's not a sustainable situation. So what are they going to do? The state had been trying to coerce the irrigators into some kind of management scheme for decades. But they have a water right, it's a property right. They weren't going to listen to the state, and they fought back. They get very stubborn when you tell them what to do. A few years ago, after decades of basically knowing there's an issue but not having a political solution to actually get anywhere to try to manage it, a couple of ranchers approached the state, and they said, "We don't want you managing our groundwater. Let us do it, but we need you to be the referee. Let us come up with a plan, and then you make sure nobody cheats." So they passed a law last year that allows the groundwater management districts to form what they call local enhanced management areas, or LEMAs. So these local groups come up with their own plan with input from the state. The state has to buy off, but then the state is the referee. So it is empowering the local people, so now they're actually coming up with ideas. And some of these ideas may seem real simple, but one of them they came up with was, in Western water law, they have a concept called use it or lose it. If you have a water right, say you have a water right for 5,000 acre feet every year, and if you don't use it one year, your neighbor can say that you did not put that water to beneficial use. You wasted that water, so they claim your water right, you lose it. So if you are going to defend your water right, you have to use all your water every year, whether you're going to plant or not. So people wasted their water if they didn't need it. So they changed that. They said, okay, we'll have a conservation pool. If you don't need all of your water, leave it in the conservation pool. We'll compensate you for your water, and you won't lose your water right. So now people are looking for ways to be more efficient with their water, and they're leaving their water in the conservation pool. So it's stretching that rate of depletion. It's just an example of how if you let the local people be part of the process, you can get around some of these political hurdles. Well, we have to recognize that you can't manage what you don't measure. So the foundation for any good management scheme is data. You need good data. We all know about monitoring wells. How many of you here know about GRACE? Okay, some don't. We'll just do it real quick. It's a couple of large satellites that orbit the planet, and they measure the distance between these satellites to within millimeters using microwaves. And if you think back to physics, what determines how a body orbits another body is the gravitational field. So if the one satellite goes over a part of the Earth where it's a little denser in the subsurface, it's going to pull that satellite down a little bit. It's going to change that spacing between the satellites, and you'll be able to see that change in the gravitational field. And the opposite happens when it's less dense. So for the first time, and these satellites orbit the entire planet, cover the whole surface, roughly every 30 days. So for the first time, we can look at the three-dimensional gravitational field on the planet every 30 days. So we can look at gravitational things that change on short time scales. They started out looking at things like tides in the ocean, circulation in the ocean. And they started looking at groundwater, because one of the things that changes over short durations is storage of groundwater in aquifers. And I have to get out of this. Hopefully I'll get back in. But I'm going to show you an animation of the United States from 2002 to 2012. You're going to see red areas are areas that are getting drier, and blue areas are areas that are getting wetter. And I think it's going to work. Okay, so here, the west in 2002, the west is kind of dry, southeast is wet. Okay, now California, 2004, it's a little bit of a drought in Southern California, dry in the west, but most of the east is doing okay. Now California is wet, 2005, 2005-ish. Texas is in a bit of a drought. California is still wet. Texas and the southeast are dry. Getting into 2007, the southeast is dry. California is in and out. Now it's getting into a drought in 2008. Texas is still in and out, but basically not too bad. Now you're going to see coming into 2010, Texas is going to come into a drought, and you're going to see, and California's not too bad. Now coming into 2012, the whole central part of the states are going to go into a drought. Okay, it's an interesting tool, and right now it's kind of qualitative. When they try to calibrate that to actual monitoring well level data, there are some places it works good and some places it doesn't work so good. Shallow aquifers have more of an impact than the deep aquifers, so it's not a great quantitative tool yet, but in terms of a tool of communicating with the public, I think it's very powerful. Another issue that we've been wrestling with for quite a while now in the United States that I guess you folks are starting to have to deal with is monitoring for oil and gas. We went through our what we call coal bed methane, but you call it coal seam methane. We went through that boom in the 80s, 90s, and early 2000s. We've had a boom in the last 4 years on hydraulic fracturing of shale, and that is driving the coal seam methane producers out of business. It's dropped the price of natural gas in the United States down below $4 an MCF. I think you're up around 12 or 14. So it's really changed the energy future, and it's like a freight train. Once it starts, it's almost possible to stop. It's hugely controversial in the United States. There are people who are adamantly, they're actually fearful of it. So it's created much anxiety and much controversy, and some of the risks have really been overstated, but there really have been legitimate concerns too. A few years ago, the energy companies were taking the approach that it was impossible for their activities to have any impact on groundwater, So they weren't going to have anything with monitoring. They did not want to do any monitoring because if you had no data, you couldn't prove they did anything, and we're not going to do anything anyway, so you don't need the data. Well, public opinion turned against them. We have had problems. We've never had a frack out. We've never had a situation where a frack has gone up and intercepted an aquifer because it's typically too deep. But we have had casing failures. We've had bad grout jobs. And we've had a lot of spills on the surface. And we've had a lot of conflict between ranchers and other users for the water they need for fracking. So now that public opinion is against the oil and gas companies, they wish they had the baseline data to protect themselves. So I guess the take-home message is if you want to avoid similar problem to what we're having, is if you can convince the energy companies to get the baseline data before they go into a basin, it really is in the best interest of everybody to actually have some facts to discuss rather than throwing around innuendo. So this is a quote from The Last Ranch by Samuel Bingham. "If the Creator divided us to prevent us from dominating His creation, perhaps He will let us come together to save what's left." Or, as I heard a high school kid on the radio say, "You can change the way the world sucks." So what are we talking about? We're talking about ways to refill that groundwater canteen for a sustainable future. And we're going to talk about a whole bunch of innovative solutions. I know some have been used in Australia, some haven't. We're using bits and pieces of these around different places in the United States. But it's the idea of trying to capture water when it's available, either surface water or wastewater or some source of water, capture it, get it underground to store it, and bring it back up when you need it. And conservation is always the first place to start. I've been really impressed with your level of conservation in your homes and in your hotels and stuff. The dual flush toilets, the low flow shower heads. I've seen that your average per capita water use is probably about half of ours. So you're doing a really good job there. I've been hearing stories, though, that you're still, maybe using a lot of flood irrigation. We've gotten away from that in the States because we just didn't have the water. So we went to center pivots and then spray center pivots. Now we're going to drip. So there's always more you can do with conservation. But if you continue to use more water, there's only so much you can do with conservation. You're eventually going to have to find new sources or use the water you have more efficiently. So one of the things we're looking at is trying to find sources of new water. This is the Colorado River Basin. So this is Wyoming and Colorado. And this is kind of the headwaters of the Colorado River. And then it flows through, from Colorado and Wyoming into Utah, Arizona, past Las Vegas, into California. And it's supposed to make it to the Sea of Cortez, but most years it doesn't because, Las Vegas, Arizona, and California take more water than what's in the river every year. The water is fully allocated since the 1920s with the Colorado Compact, where they divided up the river between the 7 states. And they used 50 years of record that were actually the wettest on history. So they gave away more water than was actually in the river. So there really is no more new water in this basin. But there's a lot of growth. There's an awful lot of growth and demand for more water. So you need to find new sources of water. So you have to look at non-traditional sources of water. So we're working with a coal seam methane producer in Wyoming who produces 50,000 acre-feet a year of produced water while he's producing the natural gas. And we're working with Las Vegas to come up with a mechanism to allow them to, and this water they've been producing, it's not been of good enough quality to discharge to the river, so they've had to treat it as a waste product and try to get rid of it other ways, like through injection and things. So we are trying to broker a deal where Las Vegas will guarantee the price of natural gas for this producer, because the price is falling down so low in natural gas that this producer may have to stop producing gas. They can't afford at the current price rates. So Vegas will guarantee them a price that allows them to keep producing gas and generating that 50,000 acre feet and treat it to acceptable levels to put it in the Colorado River. We got the law changed in Colorado where it can actually pass through the river without it being claimed by somebody else with a senior surface water right. So we're claiming this is new water. This is not part of the Colorado River Compact. This is actually new water to the basin. So it wheels through these states, and Las Vegas will take it out and use it for drinking water. Kind of a crazy patchwork, right? But it's the kind of thing that we're having to come up with to try to find new sources of water. It's not really sustainable because eventually this guy will stop, the gas will run out. But it's, it buys them 10 or 20 years of enough water for 50,000 homes. So other things that we need to look at, though, are methods of aquifer recharge, basically ways to refill that canteen. This is another good reference from the Colorado Geological Society survey, Topper et al. 2004. It's on aquifer recharge, very simply written, good information, nice graphics. They're talking about basically ways of putting water into surface water basins, recharge wells, ASR wells, capturing water, getting it underground, and bringing it back up when you need it. Riverbank filtration, I know you've been doing that here in Australia. Just the idea of putting wells next to a stream and purposely inducing water from the stream to the wells, either horizontal or vertical wells. And you get some benefits. Pulling the water through the aquifer improves the quality, takes out some pathogens, gets rid of some metals. Also gives you constant quality and constant temperature, so it's cheaper to treat if you need to. You can also use the aquifer as storage, so that even when the stream goes down, you can pump the aquifer, and when the stream goes back up, it recharges the aquifer. So it's a way of using the rivers and the aquifers kind of directly together. An example of how a new way of using this in the United States is Aurora, Colorado. Aurora is an eastern suburb of Denver. It's one of those places that's on that confined aquifer that's drawing down 40 feet a year. They have come up with a plan they call Prairie Waters. They have water rights on the Platte River, but the water rights are junior. So they can only take the water in a wet year out of the river. In a wet year, they don't need the water. Dry year, they don't have a water right that's senior enough to get any water, so they can't get water when they need it. So what they really needed was a way to capture water when they had a right to take it, and store it from where they needed it. So they put 16 of these riverbank filtration wells along the Platte River, and in a wet year, they pump the wells, and they filter the water through the aquifer, you're basically taking right from the river from the aquifer, and they pump it into some old gravel pits. And they store it underground in the gravel pits. Now, Colorado's got another freaky thing about their water law, that basically says that you have to demonstrate you have control of your water or you lose the right. So if you took water out of, let's say you took water out of a mine and put it into the river and wanted to pull it out somewhere else, if you didn't have a water right to that stream, as soon as you put that water in the river and lost control of the water, you lost the water. Whoever has the senior water right gets it. And they treat the groundwater the same way. So they had to show the state that they could control their groundwater. And they were, very reluctant to change how they think. So they ended up putting in a slurry wall around this gravel pit, 200 acres, that they had to put a slurry wall down about 80 feet. Only because of the fluke of the Colorado water law. They could have easily put the recovery wells down gradient and not needed to do this, but they had to do that. They're about 40 miles out from the city, so there's 40 miles of pipeline. They had to put a surface water treatment plant in because this water needs to be treated as surface water. So all told, it's $660 million for this project. It just went on in 2012. They're initially doing 10,000 acre feet. They're going to go up to 50,000 acre feet. Very expensive, but water is so valuable in Colorado right now that this is economic. It's $30,000 for a senior water right for an acre foot of water in the Denver Basin. So, $30,000 for 1 acre foot. These kind of things make sense. And they are just tickled with this project. Their goal is to drought-proof the city of Aurora. Another project is aquifer storage and recovery, and I know you folks are using that. The idea is to take a source of water, whether it's surface water or wastewater, and some source of decent quality water, inject it into a confined aquifer, store it as a bubble, and then when you need the water, you flip the pump on, and you pull it out, and you use it again. And if you design this bubble right so you don't get much mixing, you don't have to treat it again. You can come out and you can use it just as it is. Now, if you're storing fresh water in a freshwater aquifer, it's not that big of a deal. But if you're storing fresh water, say in an aquifer that's got iron or radium or arsenic, or let's say it's a brackish aquifer, then mixing's a big deal. So you really have to design that zone right. It's used a lot in the United States. Florida's got 150 wells and 80 systems, and there's over 500 wells in the U.S. All over the country. We had an issue in Florida with arsenic. You take oxygenated surface water and you put it underground into confined aquifers that are under reducing conditions. These aquifers have trace amounts of pyrite. That oxygen reacts with the pyrite, mobilizes arsenic. So, and in the United States, the underground injection laws say you cannot degrade the aquifer. So even though you could treat the arsenic at the surface, you're still generating arsenic in the aquifer. So they shut down a lot of these ASR systems. So we're now starting to pre-treat the water to strip the oxygen out before we store it. We've gotten around the arsenic issue. Case history here from Florida. This is Marco Island. Marco Island is in southwest Florida. It's just off of Naples. It's very southern Florida. It's a very well-to-do snowbird retirement community kind of place. Very expensive golf courses. Kind of place I used to caddy when I was a kid. They had a water supply that was shallow wells pumping from a brackish lens of water on the island that would go through RO, and that was their water supply. But as they started to develop and pump more, the water got more saline, and eventually their RO system wasn't able to keep up. And rather than going to saltwater desal, they started looking around for another source of water. Problem is they're an island with no fresh water on the island. If you go onto the mainland of Florida, all the groundwater is spoken for. People fight for the groundwater over there. So they're not going to get more groundwater. Florida gets about 2 meters of rain a year, but most of it falls in 3 months in the summer. Their biggest demand is in a few months in the winter. So they had plenty of water. It was a storage problem. Okay? Can't really build dams in Florida very easily because it's very flat. Land is very expensive, and the rock is very soluble. So you get sinkholes. So, but they do have good aquifers. So we built a system that took water from a stream in the summer when there was excess water flowing in the stream, store it in rock quarries to let some of the solids settle out, run it through a sand filter, and then inject it through ASR wells into a brackish aquifer down about 800 feet. And it's about 7,000 parts per million TDS. So it's important that you pick a zone that minimizes the mixing. So you can put it in as a bubble and pull it out as a bubble. And we're able to find a zone like that. So we get over 80% recovery at a cutoff of 250 parts per million chloride. Right now they're storing 1.5 billion gallons per year, and it's what gets them through the winter. So it's basically they built a large underground storage reservoir with a very small footprint, and they built it one well at a time. Last case history, kind of tying together all these different ideas you can use. And this is the Los Angeles Basin, basically. It's made up of 2 groundwater basins, Central Basin and West Coast Basin, separated by a leaky fault, the Newport-Inglewood Uplift Fault. And we have bedrock along the mountains to the east, some bedrock hills along the coast. But in most cases, you've got thousands of feet of sand and gravel and clay directly in connection with the Pacific Ocean. And there's over 400 wells pumping 250,000 acre-feet a year. It's a small area, about 400 square miles, but there's 4 million people. And by the 1950s, they had dropped the water level in the aquifer below sea level in half the basin. So, of course, they had a saltwater intrusion problem. In looking at it in cross-section, the aquifer consists of 2 or 3 different major aquifers separated by some leaky confining units. And here's the Pacific Ocean. And as the salt water is pulled in, the wells nearest the coast salted up first, so they stopped pumping those, which meant they had to pump the wells inland a little harder, and they salted up, and they had to move the wells inland. Pretty quickly they learned that they were just pulling the salt water right into the basin. So in the 1950s, the Water Replenishment District of Southern California came up with a great idea. They basically built a line of injection wells into these aquifers, and they injected fresh water into those wells, not to recharge the aquifer, just to build a ridge on the water surface where the water levels in the aquifer are kept just a few feet above sea level between the saltwater wedge and the main pumping center. They're still pumping below sea level in here, but that keeping the water a few feet above sea level builds basically a barrier and keeps the salt water from intruding. And one of the beauties is, because they're still pumping below sea level, most of the water they inject actually goes into the basin and recharges the aquifer. They're only losing about 10 or 20% towards the ocean to keep the seawater out. So here they can keep basically pumping the basin as hard as they ever did, and they've stopped the salt water. And they've built 3 of these barrier well systems along the gaps, and it's about 16 total miles and about 300 wells. Very simple. They have, you walk down the street and the sidewalk has got grates in it. You pull a grate up, and there might be 2 or 3 wellheads in that grate, in that pit. But a very simple system. Initially, all the water came from potable drinking water. They're moving away from that, and they're now starting to treat their wastewater with RO in microfiltration and ozone, and that is going to be their entire source of their barrier water, the barrier well water, within a few years. So we just jumped down to the next basin, the next county, Orange County. They're in the same basin. They have the same saltwater intrusion problem. They also have their own barrier well system, but they've taken it to the next level where they actually recycle 70 million gallons of their wastewater by sending it through advanced treatment, RO, microfiltration, UV. They're going to expand to 100 million gallons. They treat the wastewater, they pump it inland to these old gravel pits, and they recharge the aquifer with it. And if anybody ever goes to Disneyland and you're driving through Anaheim, you drive right by Anaheim lakes, and you'll see people out there fishing and sailing and picnicking around these things. They look like beautiful little parks, but that's treated wastewater, and those are recharge basins. They also have got a river that goes right through the county, the Santa Ana River, and most years it's dry all year. They'll have a few wet years where they'll get a big gush of water down the river, and it used to flood. So they channelized it and put, riprap and concrete banks. So now when they get a storm event, the storm water just gushes down that channel and out to the ocean, and the water's gone. So they put rubber dams in across the river channel, and there's 2 of these systems. Most of the year they lay flat. You don't even know they're there. And then when they get a stormwater event, they flip the switch, and within 15 minutes, you have a 12-foot rubber tube laying across the riverbed. And the storm flows, peak storm flows, can still crest it, but it impounds water behind it, and that recharges the aquifer. Now, this wasn't a cheap system. They spent $400 million, and they got a lot of heat for it because people were complaining that, in the wet years, it was engineers having, wasting taxpayers' money and having, having a little experiment. But then they went into a drought in 2008 through about 2010, and whereas most of Southern California was seeing their water allocations cut back, and they're going to mandatory conservation and no outside watering, and people were very upset. Orange County had none of that because they recycle their water. They have basically a drought-proof water system. And I never thought in 30 years that I would say Southern California, somebody came up with a sustainable water system. So I usually use Southern California as an example of what you should never do. But here it is actually sustainable. And there are alternatives where to get more water from the north. And in California, that has to come through the Sacramento Bay Delta, which has got huge environmental issues. They're collapsing an ecosystem. They also have to pump it over a mountain range and down into Southern California. So even though they're using reverse osmosis, this system actually uses less energy and cost. The water is cheaper than their alternative. So it's a win-win in that way. And it's not just the not just Orange County and LA County, all over Southern California. They've been doing recharge basins for decades. I used to think it went back to the 1960s. I was just out in Riverside, not far from LA, and they were telling me about a recharge system they put in the 1890s. So they've been doing this for well over 100 years because they had to. So just to wrap up, attitudes in water are changing. Historically, water has been free. You pay for the cost of delivery or the cost of treatment, but you don't pay for the water. And when something's free, it has no value, and it's not factored into economic decisions. So we have got decades of making bad decisions because they made sense, because we didn't value the water. Okay? And we have to recognize that there are dozens of cultures that have collapsed, societies that have collapsed throughout history because they couldn't manage the water. The Maya in Central America, the Hohokam in Arizona, and if you look to the Middle East, there's several civilizations that crashed because they couldn't maintain their water systems. So this is something that's really important to us. And this is a very good book on kind of the secret life and turbulent future of water, The Big Thirst by Charles Fishman. Excellent read. It's got about 2 or 3 chapters in Australia and about your drought. But this is the last paragraph from his book. Many civilizations have been crippled or destroyed by an inability to understand water or manage it. We have the huge advantage over the generation of people who came before us because we understand water and can use it smartly. Everything about water is about to change, except, of course, water itself. It is our fate that hangs in how we approach water, the quality of our lives, the very resilience of our society, the character of our humanity. Water itself will be fine. Water will remain exuberantly wet. Thanks for hanging in there with me. That's all I've got.